there are various things to discuss. So basically the next 2 lectures will be entirely on superstring amplitude. So I'm not very specific on what I will discuss, but let's see how it goes. So let's first discuss the first 3 things and then we will see. Okay. So last time we discussed poles of amplitude, and so let's consider not closed string, let's discuss. Though I haven't done the derivation, can I just discuss 4 graviton amplitude? Because I can discuss 4 tachyon amplitude, but yeah, but it's I think let's just discuss 4 graviton amplitude in superstring theory, because the basic the thing that I want to really discuss is you will see it doesn't depend on much on the derivation. Let me write down the expression and then we will go on to the discussion. So let me write down the expression. So the expression for the amplitude is, okay, so the graviton is given by polarization tensor, which is symmetric and traceless, and it also satisfies the transverse condition. So this is the graviton polarization. Okay, and since I'm not going through the derivation, I will discuss the derivation on superstring next time. So I'm not writing down the vertex operator, I'm not writing down any expression, I'm just writing down the amplitude first. So the amplitude is given by some function of the polarization tensors. So I'm considering 4 of them. Okay. Times an integral which is given by okay. So this function, you must be wondering what is this function. So this is in bosonic string theory, it's very complicated. Yeah, it's very complicated. So let me just write down the expression for superstring theory. If you want a closed form expression for the bosonic theory, I can show you, but it's very long. Well, it's also long, but I think it's more interesting in superstring, so that's why I'm writing down in superstring amplitude. Okay, so in order to do that, let me first. So this is I will in general discuss these things, but the basic point is that how do you construct effective action from these amplitudes, right? Because usually what happens in quantum field theory that we are given out the action and we construct amplitudes out of it. But here we just have a worldsheet way of deriving the amplitudes, and we want to derive the space-time action. Okay. So in order to derive the space-time actions, the first thing we need is basically the linearized fields in the space-time. So the linearized fields are, so for Graviton, the linearized field is Riemann curvature. So this is linearized Riemann curvature. Okay, and the linearized Riemann curvature in terms of these polarization vectors are given by okay, and then antisymmetrized. Sorry, which one? Okay, so as you know that Riemann curvature tensor is antisymmetric in the first two indices and antisymmetric in the second, third and fourth indices, but it's symmetric in first, third or fourth, second, fourth. So you have to appropriately take care of this in defining this linearized curvature. Okay, but this is linearized. Again, this is linearized. So basically when you go to space-time action, this is. Have you done amplitude computation in Einstein gravity? Or shall I review it? Yeah, that's why I'm saying that probably I'm going too fast. So have you done amplitude computation in Einstein gravity? Let me just review it in very short time, okay? Yes. Yeah. I'm doing it very quickly, okay? So I'm doing it only for Einstein gravity. So in Einstein gravity, the action is square root gr, okay? Let's restrict to 4 dimension. It's 3 level, so you can go to any dimension. And this r is a function of the metric, okay? So the first thing you do is first you write the metric as a flat space metric if you are doing computations around flat space plus a linearized perturbation, okay, a small fluctuation around that. So you can think as a spin to field propagating in flat space time in this approximation. So you insert this, and when you insert this, you know that Riemann curvature for the flat metric Riemann curvature. Is 0. Okay. So basically, if you do things, then if you put it back consistently, you will first get a kinetic term for this, which is very similar, which is more complicated, but similar in spirit as the Yang-Mills kinetic term, which has a lot of gauge invariances. So you have to fix first the gauge invariances, and once you fix the gauge invariances, you can extract the 3-point function. And that way, you can compute the amplitude starting from Einstein-Hilbert action. Okay, so the basic thing, in other words, if you write down the amplitudes will be so. Okay, so you may be wondering what is this connection between two. So as you have done in for scalar fields or for Yang-Mills field, this is some polarization vector times some wave, right? That's the way you do it, and that's the way you get the polarization tensor starting from the fields. So now I am starting from the other perspective. I'm starting from amplitudes, and I'm trying to I will not construct the action today, but I will anyway do that in these 4 lectures. But the main purpose is to say that whenever we write down a gravity amplitude, the suitable basis to write down on-shell amplitudes for gravity is to construct the Riemann tensor, because this is gauge invariant. Okay, so for example, if you write down a Yang-Mills amplitude, the suitable basis for write down the Yang-Mills amplitude is not the polarization tensors, because polarization tensors are not by themselves gauge invariant, but the field strengths you construct out of it is gauge invariant. So if you write down the amplitude in some polarization tensor times some pole, then the amplitude by means manifestly gauge invariant. Okay, and that's the thing we also try to do when we try to write down the amplitudes, gravity amplitudes in string theory. Okay, any question? So sorry. Yes.
Do you find any sum over all the particles?
No. So when you say do Yang-Mills amplitude, right? You just do it for a single photon, right? And 2 photon is basically 2 fluctuations separated by some space-like separation. You do the same thing here, right? You are creating these fluctuations at say minus infinity, and then you are just throwing it.
Is the curvature tensor at asymptotic infinity?
This is a curvature in the momentum space. Yes, as I have constructed, you can see this is a curvature I have constructed in momentum space. But if you construct amplitudes are always by definition in position space minus infinity to plus infinity, right? This is in a momentum space because we are doing all the computation in momentum space. So here when you construct these things out of it, you have to properly anti-symmetrize these things. Okay? And then this is a very interesting computation actually. I think everyone should probably try it, this thing. There's four graviton amplitude in Einstein gravity, tree level. Okay, so if you do that computation, you can write down this amplitude in a very nice basis. Okay, so I haven't written down anything actually. I've just written down some symbols. So this TA. So if you have 4 Riemann tensors, then 4 Riemann tensors has 16 indices, right? And these TAs are very particular rank 8 tensors. Okay, so let me basically you do is that you take this Riemann tensor, and let me write down the Riemann tensor like this: R mu1, mu2. Okay. Then this T matrix has 8 indices. And this T matrices has index mu1, mu2, mu3, mu4. And basically you contract the first 2 indices of the first Riemann tensor you constructed out of the polarization of the first particle with these 2 indices similarly. So there are 2 Riemann tensors, 2 T8 tensors, one contract the first pair of indices, second contract the second pair of indices. Okay? And this is a very particular tensor. It has a very long expression, but I will provide you that expression. I'm not writing down in a board, but it is some rank 8 tensor. Okay? The good property of this is that this structure is actually fixed by supersymmetry. But we will come to that in the next lecture. But at this moment, the most important thing, the important thing that I want to tell, because the important thing is not to discuss this polarization structure, which I will do anyway, but to discuss the pole structures. Okay. So let's assume this is something. Let's not go into that. And you can ask the question that what is the poles of this amplitude? So the poles of this amplitude is given by the poles of the gamma function. Right? That's the way you get the poles of the amplitude. But if the point I wanted to make is that if you go to 5-point function, or if you go to 6-point function, or if you go to n-point function, you do not always have a closed form expression like this. You cannot always do the integrals and write it like this. So in general, the form of the amplitude is some for n-point function. Okay, so let's say you have n-point function, so you can always fix 3 points, and for the other n minus 3 points, okay, and there is some polarization tensor or other things, but the main point is not to discuss the polarization tensors today, but to look at this expression. Okay, and the Green's function we know is okay. So you may ask the question that how to know the pole of these amplitudes? If we do not have a closed form expression, how to know the poles of this amplitude? Okay, so and this is a very general point, because you will also see that when you go to one loop amplitude, we also do not have a closed form expression like this. So we need a different way to understand that. And let me try to discuss it first let's try to discuss it for the 4-point function, okay, and in the old way. I will discuss what is the old way and what is the new way, but let's just discuss because I think it's simple. Yes. Yes, but at this point I'm just talking about general amplitude. Means you can have this form of expression, say in 4 graviton or 5 graviton or 6 graviton in bosonic string. My goal is to just discuss the pole structure, because the kinematical structure is really interesting in superstrings, which I will discuss next day. So let's discuss this amplitude, and as you can see, this amplitude, let's draw the diagram here. Okay, so on a sphere you have 4 points, one at infinity, one at 0, one at 1, and this is z, right? So now if you look at this expression, you can see that whenever z goes to 0, you can effectively ignore this term, because this is 1 minus 0 plus something small. Let's do it in leading order, and let's ignore this term at this moment. So when you go to z, when z, this variable, goes to 0, I'm just looking at this algebraic expression. I'll come back to the physical picture later. But let's look at what happens if z goes to 0. When z goes to 0, this is, you can ignore this term, and this effectively becomes right. Now let's do a coordinate transformation, and let's say log r equals log z equals to right. I agree, but I'm just looking at the behavior of the integral very close to the point 0. So when you integrate over z, you integrate over all the points, all the sphere. I agree with that. But I'm now just looking at the behavior of that integral in a near about of the point 0. Okay, very soon you will understand that what is the physical picture, but let me just do it now at the level of integrals. Okay, so this, let's say this log z is equal to s. Okay, and then this integral becomes, oh sorry, tau. Okay, then this integral effectively becomes, you will see that if, so let's say z is equal to, you can easily do the theta integral because theta is compact directions. Okay, so very near about, this is still very near the point 0, and you can see this this tau integral effectively becomes d tau exponential minus alpha prime s over 4 times tau. Okay, and this is very close. So z is, say z was less than equal to 0, sorry, not less than equal to 0, greater than equal to 0 and less than equal to some epsilon. Okay, sorry, yes, sorry, yes. Then this integral effectively becomes integral to some finite point, let's say. Okay, so let's also let me point out one more thing. So when I have chosen this local choice of coordinate, by suitably choosing the local metric there, I can make this integral from 0 to 1, right? By suitably rescaling things. 0 is unambiguous, doesn't depend on the metric, but the upper limit depends on the local metric you choose. You agree? So let me, yes, right, and the origin when you rescale remains the same. So then this integral basically becomes an integral from 0 to infinity. Okay, And this you can see as the integral, sorry? Hold on, let me see.
All z is 0.
Yes.
Minus infinity.
What? Sorry. Yes. Sorry. Thanks for pointing that out. There is a minus sign mistake here. So let me do this. Yes. I'm always.
That how can you do when you have z close to 1?
No. Z close to, okay. That's I was saying that you chose a very small neighborhood around z equals to 0. But once you have chosen that neighborhood, you now rescale the local metric in that neighborhood.
So the d square z will become d square z times.
Yes. Yeah, yes, I agree. Then it will pick up some scale factors. Yes, and the point is that when you rescale things, since this is an on-shell amplitude, the local metric factor you pull out always vanishes because it's an on-shell amplitude. If I'm off-shell, then it depends on the local choice of coordinate. So that's why I can ignore that. But you have pointed out rightly that in order to do that, I have to really keep all of it. I can just ignore alpha prime t. No, there is no ghost here. I'm just written down the algebraic expression. The ghost and everything I have taken care of, and I'm just written some complex integral on the sphere. Yes, the integral is scale invariant on z on shell, and I'm just considering an on shell amplitude.
You're doing like z going to some alpha z, so
yeah,
because z equal to 1 would become some 1 by alpha.
Yeah.
Scale equal to 1 by epsilon.
That this integral is scale invariant, but
Ignore the second term. Then you scale the
Yes.
values of z.
Yes.
And so now the integral should also get affected, right?
Yeah, that's what Prithvi is trying to tell. But okay, let's okay. If I do the rescaling at this level, so that this point at 1 becomes a very large point. Are you happy now? Let me first do the rescaling. So that is at infinity, and this at very large value lambda, some lambda, and then I am choosing a neighborhood around 0 of radius 1. Why it can't be 0 to infinity? I'm just restricting to that neighborhood. I'm just restricting to that domain. You have to integrate z over all values. I agree with that. But I'm just looking at the integration of z only restricted to that domain. It's a part of the integration domain, but it's there in the integration. Yes, right. No, that's I'm saying that I am rescaling this thing.
Yeah, so maybe you should call it z tilde. So less than equal to mod z tilde, less than equal to 1 plus z tilde some
I have to do that. Yes, and now I am rescaling theta so that epsilon becomes 1.
yeah, but finally the cutoff should be there.
The cutoff should be there, and cutoff is still there. It's 1. It's a finite cutoff. If z tilde is, so I started with an expression which was 0 less than equal to z less than equal to epsilon, and rescale things to 0 less than equal to z tilde less than equal to greater than equal to 0 and less than equal to 1. That's the only thing I have done by rescaling the local metric around that point.
Maybe I will have would have set it at 0, some large number, infinity.
Yes,
Z,
yeah, that
large number minus Z.
yeah. That should have been the best way to say that. Yeah, yes. Okay. Then this integral becomes 0 to infinity exponential. Oh God, I have done something with the signs. I missed some sign somewhere. I can't figure it out now. This should really be minus sign. I'll try to do the computation and again, and I'll probably provide you.
There's a minus sign, you get a plus over.
Yes, but that's not my main concern. The main concern is that this integral is divergent integral. This should really be minus sign here, and then
Domain of S.
yeah, but yeah, S is usually so.
S greater than 0 domain, yes.
We can always analytically continue and come back to the original domain. Yes, that's also true. Yes, so let's just stick to that. Okay. So this becomes 1 over alpha prime S. Okay, and the main point is that you have seen that when the third vertex operator, usually this is the normalized, the way people say that this is first, this is second, this is third. Anyway, the unfixed vertex operator, when it close to the first vertex operator, the zeroth vertex operator, it develops a pole on the amplitude. Okay, so that's the basically point, that whenever two vertex operators come close to each other, this log, you can basically, then you will see that, where I have written down this expression, then you will see that, let's say some z I hat coming close to z j hat, then basically you can this Green's function between I hat and j hat, which is and this is dominant to all other Green function there, and near that domain you can basically ignore all the Green function, and near that domain this integration of z correctly reproduces the pole. In other words, the two poles, the pole of the amplitude only develops when, as I said, two vertex operators come close to each other. And that also in this picture correctly explains that why you can't have S channel, T channel and U channel pole simultaneously. Because the vertex operator, the unfixed vertex operator, can only be close to either of these three vertices. Right? You agree? Let's now try to rephrase it in a different way. Okay? In different way, let me draw a big sphere. This is at infinity. This is at, let me just take to the convention 0. This is at some z. And I have chosen a local coordinate around 0. Okay? Now, as z approaches 0, you can think the z is approaching 0, or you can choose a local coordinate such that the radius, let's draw that diagram again. This is at 0. This is at some z, and let's say in that local coordinate this is at epsilon. Okay, so this distance is epsilon. Okay, so this is some z coordinate, local. Let's just say z tilde coordinate. Okay, now let me choose a coordinate w.
Between 0 and z. Okay. This is standard around.
Yes. Yeah, this is in that small domain. Okay, now let me choose a variable w in such a way And let's say at this moment the distance between these two is delta. So we choose another point such that in the W plane, this is W plane. This is W plane, and then what will happen that this in this W plane, these two point, I chose this coordinate in such a way that this distance remains same. So in this picture, this domain remains same, but you change z tilde so that z tilde approaches 0. But I trade it in such a way that here you have some delta epsilon, let's say epsilon tilde, okay? I'm not very specific about the epsilon tilde, you will see why. In such a way, as you vary z tilde in this coordinate, the distance remains fixed. If you have to do that, then what will happen? The thing that will happen is that basically this z tilde, this epsilon tilde will change as a function of z tilde. Right? In other words, when epsilon is really small in the global coordinate, you can picture this thing as like this. Do you understand this? It took me a long time to understand this, so if you don't understand this, you can ask me. The point is that let's choose a local coordinate around this, and let's not do anything to that. Okay? So there are three things. One thing, there are three coordinates. One is this local coordinate around this point, which basically becomes some local coordinate in this sphere. Okay? There is some local coordinate here such that these 2 points remain fixed as you change z. Then what will happen? Basically the separation between these 2 coordinates will grow large. Right? So then this is the local coordinate around that such that these 2 points remain fixed. And the moduli, in the original coordinate, the moduli between these 2 points, which is z, really becomes the length of this tube. Are you happy with this interpretation? Okay, good. So W rescaling is that we started with the original global coordinate. Okay. In the original global coordinate, these 2 points has some separation delta. Sorry, delta is really z tilde. Mod of z tilde, yes. And then it is a local neighborhood around this point 0. And in this coordinate, the thing that varies is the location of the point at location of the vertex operator at z tilde. And when we are varying, it will ultimately come close to it. Okay? But I want to see it in a different way. And the way I want to see it is that I want to choose a coordinate such that these 2 points remain at fixed distance. Okay? If these 2 points remain at fixed distance, then what will happen? The radius of the domain will increase because you have to scale things in that way. Right? If you really scale things in that way, this domain will grow bigger and bigger, and what will basically means this is that these 2 points which were fixed at some distance, and then this is fixed, then this domain will increase. In this picture, as you scale z, in this picture this domain will increase because I have kept these 2 things fixed, so I have to scale everything outside accordingly. Which in this global picture effectively means is that there is some local coordinate where these 2 points were already fixed at some separate distance, but here In this coordinate they are at fixed distance, and the separation between this pair of points and this pair of points is increasing. Right? That you can again choose a suitable coordinate, and that is basically becomes a tube. Okay, so basically in this domain you can choose a coordinate. This is basically an annulus, right? So this you can also think as a tube, right? This effectively, then this is the picture. This is the way you can see that as if that there is a long closed string propagating for a long distance, and that reproduces the pole. Is that picture clear? Which one? Sorry.
The global coordinates.
No. Sorry. This is I'm doing sphere. Yes. Okay. So there was already some coordinate here, which I'm not doing anything. So they're already at fixed distances. But here, instead of scaling z close to 0, I'm keeping them at fixed distance, and I'm scaling everything outside them accordingly. So then in that coordinate, these 2 points will become infinitely separated from these 2 points. As it approaches, you can quantify this statement. Basically, you can see that this length of the tube is basically log of z, log of mod z, which I effectively did here. But now I'm trying to tell you the physical picture. Log of z. Sorry, minus log of z. Sorry? Tau, yeah. Is this picture clear? Because if you understand this point, then understanding any pole structure or everything in string theory is very easy. You basically use this picture again and again in different contexts, and you will see I will use it for one loop amplitudes.
You are increasing the distance of both these points from the other pair of points.
Yes.
And that you are representing by a tube.
Basically that is the picture, and you can do that always because the whole theory is conformal. So whether two things is coming close to each other, really, when you are saying two things are coming close to each other, you are making a statement that you are keeping something else fixed. Otherwise, in conformal field theory, what is close and what is far doesn't make sense. And then I have two pictures. In one picture, I'm keeping something fixed and taking this two. I'm basically keeping this distance fixed, and I'm taking these 2 points close to each other. In the other picture, I'm keeping the 2 vertex operators fixed, but scaling everything outside that. And the only advantage in this picture is that you can very easily understand the pole structure. You can very easily pictorially see what is happening near that domain. That's the advantage. If you do integrations, whatever way you do, and originally when people did, they got the right answer. Okay, but you cannot always do the closed form integrals. I think for 5-point function, the closed form expression is not known. They are only written in terms of these integrals, which you have to do properly for extracting particular answers. But the main important answer is knowing the pole structures. And the pole structure is always reproduced when a vertex operator comes close to some other vertex operator. And in that domain, you can always have this picture such that you have at least 2 set of spheres, okay, and they're separated by a tube.
But I don't get it. Why is the length of the tube?
Why the length of the tube is ln? This is basically this computation. Yeah, this is basically this computation. Right, because basically as you were scaling things, you are basically scaling this upper limit. Sorry, means as you this is the infrared part. I am just choosing some coordinate in this domain such that this distance. So if this is annulus, okay, then here you can always map it to a cylinder, right? This is annulus. You can map it to something like this. By coordinate redefinition, by redefining local coordinates, and I'm just using that fact because I have that freedom.
This is just for the s equal to 0.
Good point, good point. So you are basically saying that what happens for the other values of s's?
Other negative. There are other.
Okay. Uh, all the poles, but he's asking the question that when s is not 0 but s is some other value, how can I see pole?
Because you will get all
the states are propagating in the tube. Basically, when you do these things, you basically have to quantize strings. This is effectively, if you think in terms of path integral, the path integral in this part of the moduli space becomes a path integral on this sphere times a path integral on the tube times a path integral on this sphere. The path integral on this tube basically becomes a 3-point function, where you basically insert some state here, and this becomes a 3-point function. You insert some other state here, this also becomes a 3-point function. And then on the tube, this becomes a 2-point function, which is usually diagonal, which will say that the state here is same as the state here. And if you do the path integral over the tube, you will see that it reproduces correct poles, all the states. And locally near the boundary, any boundary, I just showed you near z approaching 0, but you can do it near z equals to infinity or z equals to 1. Near any pole you can do these things. And more, for more general amplitudes, this is the only way you can understand the poles. Okay, so is this point clear to everybody for 4-point function? Then I will go on to say something more general about this part of the moduli space, how do you characterize them and how do you call them? Yes.
From this 2-point function contribution?
Yes, but only in this part of the moduli space, when z is very close, when two vertex operators are very close to each other. Otherwise, if z is sufficiently far from 0, 1 or infinity, all of them, then you cannot have this picture. They have some other contributions. In loop amplitudes in particular, I will see that this has this, I will discuss this as this is the ultraviolet part. But for tree level amplitude, in any amplitude, the correct field theory behavior, the correct things that is dictated by unitarity, always being reproduced by this kind of behavior of the integral, always. Okay, so then basically the argument is something like this. Let me clear this picture. That basically whenever you have a string amplitude, okay, it is some function on the moduli space of punctured surfaces. Okay, so if you have a tree level amplitude, then you have to consider the moduli space of n punctures. Okay, if you are, this is genus and this is number of points. So this is tree level n-point amplitude. Okay, and the whole point is that when you construct these amplitudes, this basically becomes some integration of some forms on this moduli space. Okay, and the thing that really differs, so you have some integral on the moduli space of some form. Some form f. So f is basically constructed out of the green function and other data you are given. So the explicit form of f depends on one string theory to other string theory, one compactification to other compactification. But the thing that is more general is that this form, tree-level amplitude, I'm just at this point discussing tree-level amplitude. This form is an analytic form. It doesn't have any pole in this moduli space. And you are integrating a smooth form on a non. So then the question is that what is the nature of this moduli space, right? If you really want to do the integral, you want to know what is the nature of this moduli space. Is it a compact surface, a non-compact? Is a compact manifold, non-compact manifold? If it's non-compact, what is the boundary? How do you compactify it? And the point is that I will not use very heavy mathematical languages, but let me just try to give you a physical picture. So what is a non-compact manifold? Is basically if you change if you go around this moduli space such that you approach a point which is not a part of that moduli space, then you call it a non-compact manifold, right? Let me try to yeah, you know all this example. Let's take a unit neighborhood in a complex plane, and let's remove a point, okay? And you can go arbitrarily close to that point, but you cannot be at that point because that is not a part of the manifold. That is not part of that space. And this is an example of a non-compact manifold. This is one example of that. So if physically you can argue that that by looking at the nature of the Riemann surfaces, if you can physically argue that when I change the moduli of the Riemann surfaces continuously, I approach a point which is really not a Riemann surface, then you are done. Then you basically have proved that the moduli space of Riemann surfaces is not compact. Right? I'm sure there are mathematical rigorous proofs, but I'm just trying to give you a physical picture of that. Okay. So if you continuously deform the moduli of the surface, and if you approach a particular type of surface which is not a part of the surface, which is not a Riemann surface, then you have basically proved that the moduli space of Riemann surface is non-compact. So then let's give a very let's say you have two spheres and they touch each other at a point. Do you think it's a Riemann surface? Just touch at a point. Do you think it's a Riemann surface? Do you think it's a manifold? Yeah, it's a singular point. So you cannot choose a local coordinate around that point such that around that point it looks like a complex plane. It looks like a two-dimensional surface around that point. Right? Do you agree? So around that point, you cannot choose any local choice of coordinate such that it looks like a complex plane. It will at most look like a cone, right? Which has a singular point. Same thing. But if they touch around a circle, what would happen? If they touch around a circle, that's again a smooth manifold, right? But you can see that as you take the radius of the circle goes to 0, you approach this particular point where two things touch at a point, but you know that's not a Riemann surface. This is an example. This is an example that moduli space of at least n punctured sphere is non-compact. Because you can approach this point, you can go very close to this point, but if you are at this point, this is really not a Riemann surface. Right? And the slogan of string perturbation theory, which many people are doing, is basically to understand the nature of the things. You will very soon understand why. The basic point is to understand string amplitude near this boundary of the moduli space. These are the boundary of the moduli space. These are really not part of the moduli space, but if you put it, the moduli space becomes compact. But they do not characterize Riemann surfaces. Okay? Yeah, I will come to that. I will come to plumbing fixture construction, but yeah, my experience is that yeah, I have done plumbing fixture construction many times, but I failed to convey the idea that why this is a signature of non-compactness. I'm just trying to make that point. Okay, so let me now characterize, as he pointed out, that what is the most general way to understand these boundaries of the moduli space, or what is the most general way to understand a local neighborhood around the boundary of the moduli space. Okay, so the most general way to understand is that, let's take, I'm just discussing one simple example. Everything I'm doing is very simple examples. I'm not giving any rigorous definitions, rigorous mathematics, I don't know even, but I'm just trying to give you the physical idea. Okay, so let's say you have 3 points, and let's say you have 3 points here, 2. Now let's choose a point, some point Z, and choose a neighborhood. Okay, let's choose a point here. Okay, before I go into this discussion, how many moduli this surface has? This is a 4 punctured surface. How many moduli it has? 1 complex moduli, right? 1 complex moduli, because you can always fix 3 points on a sphere, so it's left with 1 complex moduli. Same, there is 1 complex moduli here. Just keep that in your mind. We will come back to that point later. So let's choose a point W here, and let's choose a local coordinate around this point. Okay? Now, let's glue these 2 neighborhoods. Let's glue these 2 neighborhoods, and the way you can do this, there are many ways. There are many different coordinates you can choose. One coordinate is suitable for string theory, the other coordinate is for other purposes. But mathematicians characterize in this way. So let's glue these points by this mapping ZW equals to lambda, when lambda is a complex number. Okay? So if you glue these 2 points, there are many ways actually you can do. Okay, let me also say lambda is, oh sorry, I'm forgetting to put moduli. Okay, have you got the physical picture? Let me anyway give the physical picture. Okay, so if you do this thing, you can say, this is a very weird type of mapping. Okay, the easiest way to map, the simplest way to think about it, at least the simplest way in my opinion to think about it, is that here you choose the circle at square root lambda. Okay, here you also choose the circle at square root lambda. Remove everything from inside.
Square root of mod lambda.
Square root of mod lambda. Yeah, I'm forgetting. Remove everything that is inside that square root lambda thing. Why should you remove it? Because whatever inside this square root lambda radius in the z coordinate is outside the square root lambda radius in w coordinate by this mapping. Right? And this z is equal to square root lambda and w is equal to square root lambda are same by this mapping. So you choose this way, you remove everything from inside, and you just glue these two circles. Yes?
You remove everything from inside in one of them.
Both of them. Because the point is that everything here from square root lambda to z in this coordinate is inside this. Let me use a color chalk. Oh, it's a bad choice. Here, everything is here. And everything here is inside this. Right? So if you keep everything outside z over lambda, you don't need to keep. So if you keep things outside this circle in this coordinate, you can remove things from inside here. And in this coordinate, if you keep things outside square root lambda, you can remove these things. Okay? So in this way, then you remove this and you glued it. Okay? And then what you will get? You will get a surface sorry, it should have been small, but I'm not very good in drawing. But basically, this is a circle of square root lambda, right? And then there is a circle here, which is a circle here, and there is a circle here, which is a circle here. Is this picture clear to everybody? Oh, sorry. Oh. Okay. Oh, sorry.
We can go on, but for 2 hours.
Okay. Okay, let me try to finish this point. I probably haven't finished point 1 yet. Okay, but is this picture clear to everybody? Now you were asking me why how this tube comes in. Okay, so in this part, you can again choose coordinates minus log z. And here in this part, you can choose a coordinate minus log w. Okay? Then this annulus becomes length half log lambda, right? Because this is log, this length is in that coordinate half log lambda, and this annulus in this coordinate has half log lambda. So this in other words, you can pictorize as okay, so in this way you can see how the log mapping comes in and why in the log mapping things becomes flat and annular, and you can think in terms of pole in that coordinate. And you can see that when z becomes 0, in this picture the length of the tube becomes infinite, or in this picture this becomes a noded surface where two surfaces are touching each other. Now you can see in this picture very clearly why these boundaries has something to do with the poles. Because in one picture they are boundaries because they are touching each other. In other picture you can think it's a string propagating for infinite time, and that reproduces the pole behavior. Any questions on this? Means, have I managed to convince that why the boundary of the moduli space in case of tree level amplitude should produce the poles of the tree level amplitude? Okay. Yeah. Okay. Yeah, I forgot about that. Sorry. So in this surface, how many punctures you have? In this surface, you have 1, 2, 3, 4, 5, 6. Right? The glued surface, how many punctures you have? 6 punctures. Right? Because there are 3 punctures here, 3 punctures here, and really the puncture has been glued. So how many moduli you have here? 3 moduli. Right? And you can see how the 3 moduli, as he pointed out, coming from gluing. Because this surface has 1 moduli, this surface has 1 moduli, and this lambda, which is a complex parameter, is another moduli. So you can see that how the 3 moduli of the glued surface comes from the original surface. But I won't say. You can do that, but yeah, that's the point I'm coming, that part of the moduli space of n punctured sphere you can construct by gluing 3 punctured sphere. But
it is a part you can't get from punctured.
Yes. You will see that. So basically the motivation is that whenever you go to n punctured sphere, in the moduli, you first determine what are the boundaries. And near any local neighborhood around that boundary of the moduli space, I don't mean the neighborhood of the points, these two things are different. The local neighborhood around that boundary you can always reproduce by gluing to lower point function gluing. But there will always be some leftover of the moduli space which you cannot get by gluing to lower point amplitudes. And in field theory language, you can think those amplitudes as the one particle irreducible part of endpoint amplitude. Okay, and let me just move on. Yeah, if you have questions, you can ask me afterwards. Yeah, but I didn't realize that it's already this much. Okay, sorry. So let me now move on, and I don't think I can go to really to loop surface, but let me try to complete one loop amplitudes. Okay, so in order to compute one loop amplitude, the surface that is important is torus. Okay, and let's compute 4-point function. Okay, so I'm sure that everyone knows these things, but let me just review it. So the way you can construct a torus is that you take a complex plane and you mod it out by a discrete group action. So in other words, in the complex plane, let's say there is a symmetry z goes to z plus 1, and there is a symmetry z going to z plus tau. But tau is a complex number. And then basically you glue these sides with these sides and these sides with this side, and you get a torus. Okay? I believe everyone knows this. And from this you can easily see that tau goes to tau plus 1 is doesn't change the shape of the torus. It's just a change in the choice of the fundamental domain. It doesn't change the torus, right? Because I just choose it. And in similar way, you can also argue this is more difficult. Tau goes to -1 over tau is also a symmetry of the torus, discrete symmetry of the torus, and basically does is that it changes the two directions. Okay. Now let me introduce some terminologies which is important for higher genus surfaces. People usually, I don't think people usually much for one loop surfaces. So this direction, which is really a compact direction, you can think it as a cycle, okay, and this direction you can think it as a B cycle. So this is A cycle and this is B cycle. Okay, and on this surface you have a differential which is called abelian differential. This is given in this parameterization, this is given by dz, and you can see that integration of dz along A cycle is 1 and integration of dz along B cycle is tau. Okay, these are differentials which are regular on the surfaces. Okay, this doesn't have a pole. Again, I don't think people use these things too much for one loop surfaces, but for two loop surfaces these are very important thing to characterize things, but that's why I'm introducing all these things. And this discrete symmetry of the torus is called modular invariance. If you consider yeah, basically the point is that if you construct the abelian differential of a punctured surface, then it has simple poles at the location of the punctures. Yes. So to begin with, at this point you can think that tau is just a complex number. Okay, but if you impose this symmetry, then in the tau plane, this is tau plane. You basically can see that this is, you can convince yourself that this is one fundamental domain. And if you restrict values of tau in this fundamental domain, that already specifies the moduli space. On any other part of the complex plane, in the tau complex plane, you can just generate it by tau goes to tau plus 1 and tau goes to -1 over tau. I think there is also this thing. Okay, so this everyone probably knows this thing. So now let's go to amplitudes. I'm not deriving it. I thought I will go through some part of the derivation, but I think I have spent too much time understanding the boundary. So let me just, it's in Polchinski, you can just go through.
This boundary talks about that response to this tau to infinity region of that.
Yeah, I will come back to that.
But what is this? This is also sort of some sort of boundary.
No, because you are identifying these two things. Tau goes to tau plus 1. This identifies these two naive boundaries, it looks like. And it's a very important point is that if you are not very careful about modular invariance and things, so if you construct an amplitude which is not modular invariant, and if you restrict things to fundamental domains, then you will see that it has spurious behaviors. because you are thinking by looking at the torus that the torus has modular invariance, but sometimes the torus has modular invariance but the amplitude doesn't have, and that gives spurious behaviors and other things, and yeah, there are papers, people have discussed these things. So let me define Q as exponential 2 pi I tau, and let me define Z of x. Well, this is a definition, this you can derive, this is not a definition. This is given by 4 pi square alpha prime okay, and then I'm just writing down the expression, I'm not giving the proof. There is an important thing to discuss. Okay, before I move on to amplitudes, I should talk about green function, because if you do OP exponential ik dot x times exponential ik, so whenever you have a vertex operator, let's take the vertex operator of tachyons. So when you contract these things, you will generate the green function, right? So what is the green function on torus? That is important to compute the amplitudes, right? And the easiest way to do that, okay. So what is the area of this? Thing. There are various normalizations, and I think I have messed up normalization somehow. But in this normalization, the area of this region is just imaginary tau 2. Imaginary tau, which is tau 2. Do you agree? These two lines are parallel, and then you measure the length of the base, you measure the length of the height, and you just multiply and get the area, which is tau 2. Okay. So the important point on these surfaces is that on these compact surfaces on torus, so if you want to compute the green function, that is basically doing electrodynamics on 2 dimension, right? You put a charge on the compact surface, and you ask what is the electrostatic potential on that surface at any particular point, right? But since this is a compact surface, you cannot just put, the surface cannot have non-zero charge, okay, because it doesn't satisfy Gauss's law. Okay, so on a compact surface you cannot just put non-zero charge, whether it be positive or negative, cannot put it. But in order to have, we need to compute the green function to do these amplitudes, because when you put the vertex operators, we really need to compute the green function between a point and another point, and that is really like an insertion of a charge. So what to do? The thing that there is a very neat way to do that, and the way people does it is basically so you want to compute the green function between these 2 points. In other words, you want to compute the electrostatic potential at point 2 due to a charge in 1. But as I have said, you cannot put positive charge, or you cannot put negative charge. You cannot put non-zero charge. The way people do is that if they put a charge at a particular point, and they put equally opposite amount of charge throughout the surface. Okay, so let's say this is a positive charge, so you basically smear negative charge throughout the surface, constant density of negative charge. Then it is fine, the whole surface has charge 0. And this way you can compute the Green's function on this. Okay? Is this point clear? That why I am doing this? I will come back to that you may be thinking that I have changed the problem, so everything will change. Many things will change because I have now put negative charge into the surface. But why I'm putting negative charge, is that point clear to everybody? Okay. Then the point is that when you have negative charge mirrored around this surface, then the Green's function at this point is basically Green's function due to this positive charge, and Green's function due, let's say this is positive, and the Green's function due to this mirrored negative charge. Okay, let me write down that. And the point is that when you compute the Green's function between these 2 points, then in the modified electrostatic problem, there is a Green's function between those 2 points, but plus the electrostatic potential at this point due to this mirrored negative charge. Okay, and to compute that, but the main point is that when you have these things in string theory, you always have ki dot kj okay. In string theory computation, you always come across these things, or there are always these things. Sometimes you have delta x factors sitting in front. Okay. The point is that the effect of this negative charge in both the cases is 0. You can argue that in this case, using on-shell condition and momentum conservation, the effect of the smeared negative charge is 0, it decouples. And for these del x things, when you hit that potential with a del x, because since this is a smeared negative charge, it just kills it. Okay, so though you have modified your electrostatic problem to get the Green function, but in case of physical string amplitudes, it doesn't change things. Okay, so the Green function on the surface is really satisfies this equation, del bar del I have some other properties too, I haven't listed that down. This is the part you expect, right? This is the part you expect because of its Green function. But then there is an extra part. Okay? And this is really proportional to the 1 over the volume. This basically says yes, mirrored negative charge on the surface. Okay. So this is one way to derive the Green function. And there is another way to derive the Green function is basically, another way you can do is that you know the Green function between the 2 points on a complex plane. Right? You know the Green function between 2 points on a complex plane, which is log z1 minus log of z1 log of modulus of z1 minus z2. And here you have a discrete group action. So you go back to the favorite techniques in electrodynamics, which is the method of image charges. And you basically generate all the image charges. So the Green's function between 2 points on a torus is basically Green's function this point and this point, and you generate the image here, you generate the image here, and you sum over all the images. Okay, but if you do things in that way, you will see that you will come across a divergence, which is same as the divergence if you try to solve the Green's function with a positive charge. And that you can regulate and subtract of the divergent pitch, which is same as adding this part. And you can evaluate the Green function. You can compute the Green function even in that way. So you can do things in 2 ways. Okay. I'm not going through the derivation. That's that. And then let's write down the amplitude. So let's compute. I will just discuss 4 tachyon amplitude, because 4 tachyon amplitude in closed string theory historically very important. The amplitude is given by so on a torus there is a conformal, there is only one conformal killing vector and you can fix one vertex operators. So I am fixing the fourth vertex operator on this position and 3 vertex operators I have to integrate over, and there is a partition function here which I had written down in the previous slide. It's basically z x of tau modulus power 48. Anyway, let's. I will just try to discuss the point. I mean, you will easily find this expression in Polchinski's book, but let me try to say two things. So, as you have seen that when this firstly in this expression is modular invariant. Since this modular invariant, you can just restrict your integral to the fundamental domain. Okay, and let me draw the fundamental domain again. Sorry. So you can see in the fundamental domain, the point where tau goes to 0 is not a part of the fundamental domain. In other words, the limit when the shape of the loop, the length of the loop goes to 0 is not a fundamental domain because of modular invariance. Okay, so the region in field theory which is ultraviolet divergent, in which the size of the loop goes to 0 size, is not there in string theory. Sorry? The point is basically, let's say you want to construct a field theory, and if you compute 4-point function scalar phi cube theory, and then when you do things you can do in many ways, but if you do it in Swinger parameter representation, and if you have a Swinger parameter here tau, then you will see that the high momentum ultraviolet divergence, which comes from momentum integration in the Swinger parameter. So if you go to Swinger parameter, you integrate out p. Now the only thing that is left about to integrate is the Swinger parameter. In the Swinger parameter representation, the ultraviolet divergence comes when tau goes to 0. Okay, so when the size of the loop goes to 0. When I'm trying to say, because of modular invariance, that size of the loop in the modular invariance in this way is not there. In other words, a string theory loop cannot be arbitrarily small size. Because whenever it is small, you can go to some other description where tau goes to -1 over tau, it's a big loop. Right? So this string.
Why are you identifying this tau?
Oh, okay. Sorry, I shouldn't have written it tau. I will come back to that. I will come back to the relation, but let me write it.
Draw this conclusion.
Okay. Okay. Let me try to do that. Let's say the Swinger parameter here is t. Okay, and the most naive way to think is that you are as if thickening the lines to tubes, and in that way, the length of the tube really becomes tau 2. Okay, so you can think in this way. Let's say this way. So this is basically, you can think as a thickening of the word line, and then basically this is a this is a tube of length tau 2. Okay, but as you have seen, because of modular invariance, that this way of thinking it's not It's not correct. It's only correct in some part of the moduli space. Because the distinction between the thickening direction and the loop direction basically mixes because of modular invariance. Right? Modular invariance interchanges A cycle to B cycle. So if you think that a world line has thickened and it is going for length tau, you can equivalently think this direction as loop direction and this is a thickening. And that is true because of modular invariance. So this analogy when I was trying to make connection between loop amplitude is naive. If you really think in that sense that this is a thickening and this length of the loop is tau 2, and then the tau 2 integral, the part of the moduli space is not there. That's a correct argument. But then you can ask that what is really happening, as you asked that how these two things are related. These things are related. I will come back to this point that you will see that why I am making this analogy, because this analogy, the relation between the field theory description, the infrared description, and the string theory description matches in the infrared, the part which is governed by unitarity. And in that part, you will see that there is a clear connection between tau 2 and t. Yes. It will reduce to some loop, and in that loop you will see that the length of the loop is basically tau 2. But that is only true when tau 2 is very large. Then I cannot push interior into the moduli space. In the same way, I cannot, you have seen that when I reproduce the poles, they have to be really close to other vertex operators. In other reason, the field theory interpretation is not correct. Okay, so I'll come to that. But let me say one more thing before coming to that. So this is firstly modular invariance, and modular invariance removes the ultraviolet divergence in one loop amplitude. And this is basically a very general theme, that modular invariance removes ultraviolet divergences, and only divergences in string theory come from the boundary of the moduli space, which are infrared divergences. But before going to that, so this is an one loop amplitude with 4 points, and in bosonic string theory it is ultraviolet divergent. You don't need superstring to make it ultraviolet divergent. This was shown by Joel Shapiro in 1972, and I think this is the first time modular invariance came into string theory literature. Okay, so you don't need ultraviolet, you don't need supersymmetry or superstring amplitude to make it ultraviolet finite. Then why do we should at all care about superstring theory? Firstly, there is no fermion, so I'm not thinking about that. Secondly, there is tachyon. I'm also ignoring that issue. But there is one more issue here which is very important. The thing is that, so there is a fourth vertex operator which is fixed at tau. And there are 3 vertex operators moving around. Right? So then there is a particular region of the moduli space where all the 4 vertex operators are basically very close to each other. It can happen, right? It's a part of the moduli space. And in that part, the amplitude looks like this. Is this point clear? Why this amplitude should look like this? I'm talking about the part of the moduli space where all the 4 punctures are close to each other. And then by the similar trick, which I basically discussed for a long time, you can see basically characterize that part of the moduli space as a sphere glued to a torus via a long tube. Okay? By momentum conservation, k1 plus k2 plus k3 plus k4 is 0. Right? So this is basically a tadpole diagram. This is some 0. This is in field theory. You can think like this as there is some 4-point function. This is really a 5-point function. Sorry. Connected to a tadpole diagram. And since this is a tadpole diagram, for the tachyon tadpole it's fine, but for the dilaton tadpole it's, so whenever there is this propagator is basically 1 over p square plus m square. Okay, since p in this leg is 0, this is not there, and you have dilaton in your theory, massless scalar, so m is 0. This is basically sitting over 1 over 0. So we have a dilaton tadpole, which is a signature that the the theory doesn't have a stable vacuum. And that basically is the divergence of one loop amplitude of bosonic string theory. And that is the thing that you can cure using supersymmetry. So when you go to supersymmetry, you can show using supersymmetry that this one loop dilaton tadpole vanishes. And that's why you need supersymmetry. You need supersymmetry to cure the infrared behaviors of bosonic string theory. Okay? Is it? It will be there, but you can show that this one loop, this amplitude, it's 1 over 0 multiplying something, right? And that is 0. That is non-zero. In other words, 1 point function of a dilaton on torus. This is 1 point function of a dilaton on a torus. That is non-zero in bosonic string theory, but that is 0 in superstring theory because of supersymmetry. Okay, so that's why superstring theory is important, that you need supersymmetry to cure the infrared behaviors. And let me just conclude by saying something about the infrared behaviors. One more infrared behavior. This is one infrared behavior. So you can have other type of infrared behavior where two poles, these are very interesting things, and again I can go for 3 hours, but let me not do that. What can happen is that two poles come close to each other, right? And in that part you can think this like a 2-point function glued by a propagator to one loop 2-point function. And this careful analysis is very important for understanding the one loop behavior in type 2 theory, because there is no infrared problem, the vacuum is stable. So you need to understand these things to understand low energy limit. If I have time, I will go through that in detail. But there is another infrared behavior, which is basically you take the torus, you consider the moduli space where tau 2 goes to infinity, okay, in such a way that z1 over z2, z2 such that the ratio of z1 over z4, z2 over z4 and z3 over z4 are fixed. Z is the position of the unfixed vertex operator, and z4 is the position of the fixed vertex operator. So we are scaling you are taking the size of the torus very large, and you are also at the same time you are also distributing the vertex operator so that no two are close to each other. If one of them are close to each other, this kind of thing can happen. If you do that, that part of moduli space you can think as field theory amplitude of Schwinger parameter tau 2, and these positions, the positions of this is basically imaginary part of Z. Okay, imaginary part of Z, yes, imaginary part of Z. Okay, is this point clear? Probably I was too fast. So that's why I said that this relation between tau 2, the reason that tau 2 is not equal to 0 and the ultraviolet divergence is not there, that motivation is really coming from the infrared behavior. That if you really try to think in terms of loops of some length, then if you push the 0 size of the loop, then you will see that the 0 size of the loop is not there. And that is not there because of some stringy behavior, which is the SL2Z invariance, modular invariance. Okay, so yeah, let me finish here. If you have questions, I can just clarify a few things, but I will not discuss anything more.